with yellow. I'm with pink and yellow. All right. All right, so last time we talked all about photons, and we derived finally the black body spectrum that I teased you with in the first day. I want to mention something which is in the book, and I just want to expose you to it. It's that I derived the Boltzmann probability distribution, the Boltzmann distribution where we simply said the probability of something is energy e to the minus energy over kt. And then I said, well, that actually is only quite true for particles that are distinguishable. When they're indistinguishable, I actually derived it for photons. So the point is we really should put this into a context. There's basically three distributions. There's the Boltzmann distribution for classical particles, distinguishable particles. This is the Boltzmann. And I usually wrote it as a probability times some constant. Let me call this a different constant. This would be the number. And the book is, well, unfortunately, and I hope it isn't confusing, the book and actually me, myself, have been a little bit all over the map with notation on this chapter, simply because there's a lot of different meanings of averages that are n, basically. In this table, I'm going to write it as little n. So this would be the probability times the total number, and perhaps I've divided by the unit volume. In any real calculation, though, if you know how to find the constant out front, then these sorts of questions disappear. I mean, one reason I'm not sweating the fact that I've changed terminology a little bit is if you're stuck worrying about a constant like that, you're worrying about the wrong thing, right? You really only have to be focusing on this term and thinking about how to set things up. Okay, for the photons, there was actually no constant that's rattling around, and it was energy over kT minus 1. So these are bosons, all right? And I'm going to modify this a tad. The book puts in their label, they put a constant here, B. But B can be written as e to something else, and that's the standard way to do it, where mu is called the chemical potential. Now, I don't want you to memorize this formula. I just want you to realize that it is a Boltzmann-like term. If this term is bigger than 1, this thing looks like that. And there's a term which you correct for, the chemical potential. It basically is, yeah. Well, the mic's not on, sorry. The chemical potential is the energy cost for a particle coming in or out of the system. So I don't have actually a fixed number of particles in the box, but I have some particles which might jump into the box, or I have some particles which might jump out of the box. Not if it's an infinite leap box, I mean in some other situation. And if there's an energy cost, a little energy barrier to get in or out, that works out to be this little term here. And it just modifies the energy. And I did derive this, but ignoring mu. And in the appendix, the book actually derives this with the mu. Okay? And then there's another form. And the bosons, remember, these are the symmetric particles. These are the integer spin particles. And the photons are an example of it. If a particle is massless, this thing is always 0. Mu is always 0. Anyway, and then there's another expression for, which looks very, very similar. There's one simple little minus sign. This is for fermions. And just to give you terminology, this was called actually the Bose. So Bose was an Indian physicist, mid-century. Bose-Einstein distribution. And this is called the Fermi Dirac distribution. And let me just stare at this mathematically a second. Oh God, all this previous chalk dust. Fine. If I have that term, Fermi Dirac, okay, it turns out that the right analysis is the following. Energy and potential are typically, one or both of them is going to be much greater than kT. The energy might be really, really small, but this chemical potential, in almost all cases with a Fermi-Dirac system, and what's a Fermi-Dirac system? Electrons in a solid. Okay, today I'm basically going to talk about a metal. This term, even if energy can start at 0, right? The lowest energy states in a box with electrons in there is going to be 0, but this term is always much bigger than kT. And if that's true, this term is always going to be interesting. This thing is going to be big, a big number, but maybe positive, maybe negative. If E is greater than mu, then this is going to be and E is much greater than kT, then can you see that E is going to be 1 over e to the E over kT plus 1 is going to go to 0. Okay? On the other hand, if E is less than mu, then N is going to approximately be 1 over e to the minus mu over kT minus 1, plus 1. This is terrible. Can you see this? All this previous chicken scratch? Oh, boy. Oh, I'll change to pink. I'll match my shirt. Oh, I've got blue. I'm going to go colorful for the last couple days here. I'll go pink. This is 1 over e to the mu over kT with a negative sign. And that's 0, e to the negative a large number, so this is 0. So there's actually the Fermi-Dirac, it's a little bit subtle, this argument. I mean, it's straightforward mathematically. The subtle part was I had to argue that you got to think about this condition. Yeah?
It's going to 0 as what goes to what?
I'm sorry, that's not 0, that's 1. That's 0. The color change confused me. E to the e over kT, that term is big, dominates the 1 over big, 0.
So that says energy goes to infinity?
No, all I had was the following conditions. That one of them, let me write it a little more carefully. I have that mu is always greater than, actually, strictly speaking, that's all I really know. Mu is much, much greater than kT. Okay? And I'll justify that in a minute. Okay? If mu is much, much greater than kT, and just simply if E is greater than mu, then E is also greater than kT. And so this term becomes 1 over e to the e over kT. This dominates over the 1, and that becomes 0, because that's big. If E is less than mu, I don't really care about E anymore, except when E is exactly equal to mu, then this is 1 over, E is small, it's minus mu over kT, it's a negative number, very large. This piece drops out, and I have 1 over 1 is 1. Okay? Straightforward. Why I wanted to say that was subtle, but I'll sort of justify it after the fact. I'm going to use these assumptions, and then I'll show that they result in something which justifies that assumption. So the way people like to graph this is versus energy. Here's mu, and mu forms a dividing line between, on average, expecting to have an electron in this state and not expecting to have an electron in this state. I didn't quite put that right. If I have a transition, this energy equals mu is going to be right in the center of it. Now, I'm ignoring spin here. Just because these are electrons, and for every state I can put a spin up and a spin down in. In fact, there will be 2 electrons. But just by convention, when we talk about this, we only talk about, we ignore that, and we leave that aside for the moment, and we talk about there being a number 1 in front of all this. Just one particle in the state. And I don't want you to sweat this little bit. It is straightforward with that assumption, but I want you to remember this. And of course, this matches what we've been saying. I've been saying all along that when you have these fermions, because you have to anti-symmetrize the states, they have to go in and, each one in another energy, another energy, another energy. This really has an impact. This really has an impact, okay? Let's think about a metal. I'm kind of going to go in a certain order here. I want to talk about why a metal is a metal in a moment. But for now, let me just tell you that in a metal, I basically have a lot of electrons which are in a given, what we call a band in a solid. But let's think of them as a bunch of electrons sort of in a box, particle in a box style. And that is basically how you treat them. And they actually, you don't have to worry about the fact that they interact with each other. Okay, and that's a subtlety. But we're not going to worry about that. We're just going to stick them in there. So in fact, what we're going to do is we're going to calculate something called quantum gas. I mean, it's kind of cool because you can say you calculated a quantum gas. So basically what I mean by quantum gas is that it's a bunch of electrons. I'm going to do it for fermions, so let's call them electrons. I'm going to calculate, I'm put a bunch of electrons in a box, and I'm not going to have them interact. They're just going to have particle in a box boundary conditions. And as I mentioned last time, it turns out that's what I always want to do with these quantum systems. Okay, so I have the particle in a box. That's what a PIB means in this case. Particle in box boundary conditions. And I just drew it. All right, and so that was that m lambda over 2 is equal to L. And so let me try to redeem myself from yesterday where I did 2 lines of algebra and made about 3 mistakes. That's 2 over lambda times L, which is 2 pi over lambda times 1 over pi times L, which is k, well, that's k, so this is L over pi times k. Okay? That's what I did last time, badly. And that'll apply for x or y or z. It's the same argument, just repeating it. Okay? And so therefore I also want to say full m squared, where this means, where m means the, the magnitude of the m vector made out of x, mx, my, and mz, is L squared upon pi squared, k squared, where k squared is the full k vector. Okay? Let me pop over to here and continue with this. Now, so let me write that down. M squared is L squared over pi squared k squared. I also have that energy, which classically I think of as p squared over 2m, in quantum mechanics is h bar squared k squared over 2. Oh, I don't want to confuse the mass with the number m, so this is capital M. I mean the electron mass. Okay? Now what do I want to do with these? I want to find the density of states again. And I make the same argument that the number of states between m and m plus dm is equal to, I have this view that I'm in m space, where this is mx, that's my, that's mz, that's a vector m, and I have a spherical shell, and I take a thickness of it, and the thickness of it, that volume, it's in numbers. It's in numbers, and so the volume of that is a number of numbers. It's the number of states. It's an eighth of 4 pi m squared, but there's a factor of 2 because spin up or spin down. Okay? So I did this before, pi m squared. Oh, times dm, sorry. So this is pi m squared dm. I'm just repeating what I did yesterday, or Wednesday. And I can change this a tad. This is a slightly different way of talking about what I talked about before. I went from the number of states between m and m plus dm, and now I've written it in terms of a range dE. And so clearly that is the density of states, because this thing multiplied by dE is the number of states, well, between an m and an m plus dm, which has an associated E and E plus dE. Okay? So I now have the density of states. Density of states equals pi m squared dm dE. Okay, but things are a little different because this is not the relationship I had before. This is the relationship for electrons, not photons. So let's just work it out. I want to plug into this formula for K. So if this is true, this implies that K squared equals 2 capital M E over h bar squared. And therefore m squared equals L squared over 8, I'm going to plug in this there, over pi squared h bar squared 2 m E. And take the derivative of this, 2m dm equals 2 L squared over pi squared h bar squared m dE. The 2 cancels out. If this is m squared, m equals root 2 L over pi h bar root m root E. And so finally, I wanted to preserve this drawing. So combining these two, d of E equals pi, well, m squared dm dE is pi m times m dm dE, so it's this term times that term. It's the L over pi h bar cubed, pi times L cubed over pi cubed h bar cubed. I have m and a root 2. I have a root 2, I have an m to the 3/2, and I have root E. Let me see, this was m dm, and the dE was there. Here I wrote it as dm dE, so I'm just dividing by dE on both sides. Okay, so that's it. You don't need to memorize that, of course, but it's a calculation of density of states, and it worked out a little differently. The particle in the box boundary conditions were the same, but when I got to relating the energy to K, it was a little different, and I get a different formula. And that's for an electron. Now, I wanted to do this partly just to show you another calculation of this sort, but also, let's combine it with this. Remember, I said that in general, for some average for some quantity Q, now that we're in this new regime, what we're going to do is we'll take the variable Q, and we're going to multiply by the number of states at some energy. Then we're going to multiply by the density of states at that energy, dE. And if this weren't normalized, we'll just go ahead formally and write down the normalization of it. And then that's going to be an average. Okay? Actually, for these quantum distributions, the normalization, oh, I erased them, but the normalization is already done for you. You don't need to do this. You don't have to divide by the denominator. So there's a number of things I could ask. A corollary to this, which is to take the average of something. So for instance, I could ask the average energy. Okay? I could ask the average energy of the electrons in this gas. I don't want to do that. I want to ask a very particular question, and it's the only one I'm going to ask, and then we'll move on. I'm going to ask, what happens if I ask what's the total number of electrons? What's the total number of electrons in this gas? Oughtn't it to be the number of electrons at a given energy, which here, which is just the Fermi Dirac distribution, which had that mathematical formula we wrote, times density of states. How many states at a given energy? That's all. That's what it ought to be. If you like, this is just the normalization term in the bottom. All right? That's all it is. Well, I don't want to plug in. I don't want to plug in this. I don't want to plug that in because that's going to be an ugly thing to integrate. Basically, I'm going to say, oh, this is approximately equal to just integrating up to mu of density of states, and just saying it is that the number is just 1. And in fact, I'm going to give mu a slightly different name in this context. It's just by convention, we call it the Fermi energy. All right? And so this is all of this stuff. One thing that we've seen now a couple of times, this L cubed is in fact just a volume, right? All right? So I'm going to drop these constants which have been running around. So this is some constant, but I'll keep the volume because that's interesting, times the integral of e to the 1/2 dE from 0 to E Fermi. So this is just some constant, whatever constant that is, which is root 2 over pi squared h bar cubed m to the 3/2. That's what this constant is. It's still there. E to the 1/2 integrated, it was a 2/3 times the constant. What I really want, though, is the volume is there, and then I get e to the 1/2 integrated as e to the 3/2 evaluated at 0 in E Fermi. And this was the total number of particles, n. That's what I wanted. So finally, E Fermi to the 3/2 is going to be 3 over 2c. C is that constant. N over V. Or Fermi energy is proportional. I'll drop the constant to the 2/3. I wanted to show this to you because it's just to show you first off that it's straightforward to calculate. And now let's talk about the result. The Fermi energy, maybe not surprisingly, it's proportional to the number density. This is the number of electrons in the box divided by the volume of the box. Now the box is going to literally, the cases where this applies are basically metals, where there's a bunch of electrons in a band, and they're essentially all in one big state, one big set of states they can be in. And so what's interesting about this is now, the boundary conditions gave me a way to count. It told me how many electrons at what energy. And basically, the electrons just added up, boom, 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 and they filled up to some point. And then you get an energy a transition energy from their being an electron to not being an electron with a higher energy. And that's this number. What's interesting about it is if you go calculate, the book uses a silver atom as an example. And really, how does the nature of the metal, not silver atom, but a silver, I said atom? Silver metal. So if I have a chunk of silver, the thing about the silver is, right, the density of it's going to give you an N over V. And if you plug in all these numbers, E Fermi is about, it's 5.5 eV. That may not mean much to you. But one of the things I asked you to show in your homework is that for classical particles, and this basically applies to also Bose particles, even if they're quantum mechanical, typically an energy is comparable to kT. In fact, the equipartition theorem is that the average energy in a mode is half kT, right? I asked you to show that the result for the maximal Boltzmann distribution of velocities in a gas is that, okay? Do you guys know what kT is? Well, so first off, this is a point I think I hadn't really stressed much to this, in this class. And you may know this, but I can't, this bears repeating. If you don't know this, you should hear it. And if you have heard it, you should hear it again, right? If you ask, what is the energy of atoms at a microscopic level, what is the energy of any little particles in a macroscopic system? The answer is, if you know the temperature, you know their energy, okay? It's usually, well, except for some cases we're about to look at, it's kT, or half kT, okay? kT, if T is room temperature, you guys have any idea what that is? You can pop out your calculator. 1.38 times 10 to the minus 23 joules per Kelvin is K. Plug in 300. Convert it to electron volts. The answer is at 0.03 electron volts. I've mentioned that the scale of chemistry is about an electron volt, really a little bit less. We've seen that an electron volt is 13 electron volt is the depth at which, or the energy by which an electron is bound into hydrogen. So electron comes in, it falls down, it has kinetic energy now, but it has a strong negative potential, and the sum is 13 electron volts deeper than when it was free. That's 13 eV. But see, chemistry is now dealing with not the 13 eV, but between subtle changes between outer shell electrons. And it turns out it's typically somewhat less than an eV. Most chemical reactions don't really happen that fast at room temperature. They happen even less faster in your refrigerator when I take it from 300 Kelvin to, say, 270 Kelvin, okay? But they're on this scale, so a fraction of an eV even to less than that, all right? This is 5 eV, 100 times bigger. In fact, that 5 eV may not sound like much energy, but it really is. The electrons at the outer shell, so the highest energy electrons in a metal they're actually going almost relativistic speeds, okay? Well, they're not, that's an exaggeration, but they're going darn fast. If you try to turn this into a temperature, this is essentially 50,000 Kelvin, all right? So that's the result of having to pile all these electrons in a gas. If I put a bunch of Bose particles, integer spin particles in a box, they're all going to sit there, if the box is at 300 Kelvin, they're going to sit there at 30 milli electron volts. That's 0.03 is 30 milli electron volts. And indeed, that's the typical energy of an atom in your body, okay? But the electrons in your body, well, you don't have a metal in your body. If you're wearing a ring or you got a watch on, the electrons have 100 times more energy because they had to pile up in this Fermi Dirac way, okay? Okay, so then that's the last application I've made of straight StatMech. I'm closing out the StatMech chapter with this sort of derivation and discussion. Any questions? Yeah. d of E was m times dm dE. M had square root of E. M dm dE had no E in it. I just simply multiplied this equation times that equation. That's all I did. And there's a pi there. Any other questions? Yeah.
Is time considered a degree of freedom?
Is what?
Time.
No. Is time considered a degree of freedom? No.
That would make things have different energies in the past and future.
Yeah, that way lies madness. Oh boy, I'm sure someone smarter than me could go on and on about this. I mean, one thing is, wow, okay, since you mentioned it and since we're closing out quantum mechanics, StatMech, a lot is made of the entropy of time from the arrow of time based on entropy. Have you heard this argument? That basically, so I'm just going to talk about this, all right? There is one thing that's very interesting. If you think about laws like F equals ma, if you use F equals ma to solve throwing a chalk up in the air and catching it, the equation for going forward and the equation for going backwards are identical, effectively. And I could spend some little time really proving that to you by just showing that, well, if I put a negative sign there, it'll be a negative sign there, and it just cancels out, okay? And there's more and more formal ways of talking about that. As far as we know, essentially, almost all laws of physics are what's called time reversal invariant. And in the more modern sense of quantum mechanics, the way you would do it is you write down the Schrodinger's equation, and just literally every time you see t, you put in a minus t. And then you see that it all cancels out. And so people talk about the principle of microscopic reversibility. If you have little particles doing their thing, the clock could have run either way. And then there's the realization that this treatment of statistical mechanics, and I think it is related to your question actually in a way, was hinged on the idea that systems will end up randomly in the most likely outcome. And how do I quantify the most likely outcome? I write down W, Boltzmann's insight that I should figure out a way to count the number of states. And then I should figure, and in that notion, time is kind of stuck in. I actually brought time in. How did I bring it in? I said, systems ought to end up. Okay? That was where I brought time in. They ought to end up there. Because I had the notion that what really happened is the system just sat there for a long time doing its thing, and randomly it ended up in the most likely outcome, which was the one that there's more ways it can be that way. The energy for which there can be more ways that it can have that energy. Or the set of configurations where there's the largest number of states, okay? And I don't know, I actually have always been a little underwhelmed by how deep all this is. But I don't know, maybe other people think it's really neat, so let me just say it. So there is this neat idea that the fact that systems always end up in this most random possibility ties into a deeper statement of the fact that entropy always increases in systems. And I didn't really go there. We could have spent some nice time talking about that. And I mean, in fact, that was becoming obvious when Carnot figured out his statement of the second law of thermodynamics, which involved the efficiency of engines. And it's related to the notion that entropy always increases. And so the fact that entropy always increases is often said to be the only physical law which has a direction of time. Time goes in the direction that entropy increases. And that's so that entropy provides the arrow of time. Okay? So in that statement, your question was just kind of ill-posed because What I meant was I just considering the configuration of the system to consist of where the particles are and what energies they have, right? And then I just imposed that I'm going to let time go forward, and they're going to end up in some other configuration. If they happen to start in an unlikely one, they're going to move to a more likely one. And then I'm going to quantify everything by talking about the likelihood. And so in that statement, I certainly wouldn't, I mean, I just sort of by construction of that idea, it wouldn't make any sense to stick time in as part of what I consider to be a degree of freedom. Okay? That's a good question. Any other questions? If you ask me questions, I won't write equations. All right. In fact, I'm pretty much done with no, not quite, but I'm almost done with equations. So, okay, so we're closing down statistical mechanics, and I'm going to try, boy, don't have much time left today. I'm going to try to breeze through a couple of topics before we quit. And more fun. I think I will give you one sort of not very difficult homework assignment. Just make sure you're here the next few days. I'm alive. Okay. So there's really in modern physics. Okay, this is the basis of modern physics, what you've done so far. Quantum mechanics, which extends to particle physics, but it extended to explaining atoms, which extends to something called solid state physics and stat mech. All right, so let's talk about solid state physics. So solid state physics are now, I guess the modern term is condensed matter physics, because people have begun to realize that not really liquids, but all sorts of squishy systems, i.e. plastics, really, are very, very interesting in and of themselves. And certainly, there are now plastics which functions as electronics devices. You can make electronics out of plastics. That's actually a fairly big topic of research in this department. So we call it condensed matter physics. And so condensed matter physics basically means let's look at not just individual particles, but materials essentially, but at the physics of them. And so let me just let's start with the simplest thing that's not an atom. Let's start with a hydrogen molecule. And I just want to talk qualitatively about it just a moment, and then we'll quit. So if I have a hydrogen molecule, that's two hydrogen atoms. So here's a hydrogen atom, here's its potential. So this is the potential, U, for a hydrogen atom, right? If there's a proton, and what am I drawing? I'm drawing the energy of the Coulomb energy, right? And I also can think of, I have a wave function. This is sort of the S wave function. That is one way of drawing it. It was just this exponential in radius. And here I'm just kind of drawing the radius out in two directions, right? The book draws it, I mean, if I did a three-dimensional thing, this is just a sphere whose density is increasing right as I go to the center. If I actually include the fact that the volume element was, remember, 4 pi r squared dr, that will cancel this divergence at the center. So don't worry about the fact that it shoots up, okay? But the potential looks like that. Okay, that's kind of messy. Let's wait. Oh, that's psi, and that's u. Let's just kind of wave our hands at it and say, nah, it's just a hump, okay? Just to make it simple, all right? Because really what I had to do is I had to write down energy times the combined wave function is minus h bar squared over 2m del squared 1 plus del squared 2 on this combined wave function, plus the potential, the mutual Coulomb potential between electron 1, electron 2, proton 1, R electron 1, R electron 2, R proton 1, R proton 2. So there's no longer just this Coulomb potential, there's the mutual Coulomb potential between the four particles. And I got to multiply this times psi 1, 2. And basically, this cannot be mathematically solved analytically. Okay? So everything I'm going to show you was developed in the 30s, and there was no numerical calculations. There is a whole branch of science. Sometimes it goes by the label quantum chemistry. Basically, of people who solve this, and not just for hydrogen. I mean, they'll solve it for some technetium interacting with francium, right? So, Z70 with, all these electrons and these real complicated orbitals, and one atom interacting with another atom, making some bizarre molecule. And people can do incredibly well now in actually calculating with numerical techniques in the computer, solving the Schrödinger's equation, finding the wave function for all these particles, and actually predicting what chemically these materials are going to do. It's a whole branch of science, okay? We're not going to do that. I looked at it and said, let's kind of make the wave function just look like a hump. Okay, that's a little easier. All right, so here's here's proton 1, and here's proton 2, and here's a hump for wave function 1, and here's a hump for wave function 2. You got to pretend the humps are the same. And let's just talk a little bit. The total wave function ought to be psi1 plus psi2, or ought to be psi1 minus psi2. Right? Now, a wave function, if I have a negative or a positive sign out front, I don't care about a wave function, I care about a probability. I'm going to square it, and the sign goes away. But if I combine two wave functions, I think you've seen this before, when I square these, that's different. The cross term is different, okay, when I square. So those are different, that's different ways to combine the two wave functions. Quite literally, that is simply, in this case, doing this plus this. And in this case, it's doing this plus that, okay? And when I combine them, and what I'm going to think about here is that the typical size of this wave function is A0. Remember, for hydrogen, that was the characteristic dimension. We calculated it. It's the Bohr constant, the Bohr radius. It's 0.529 angstroms, which is a number you ought to commit to memory. And there's some distance r between them. If r is big compared to A0, none of this matters. It's two hydrogen atoms. They're just separate. If r gets close to A0, then this is where all this comes in. So I'm thinking of this as a function of the distance between the atoms. So let me bring the atoms in close together. And basically, as r goes towards r0 from being large, this forms, well, a bigger hump, okay? Where here's the two protons, 1 and 2. But this state forms, if I combine those two, I'm going to get something which has a node right in the middle, right? And I'm waving my hands at it, but we can get real rigorous. We can go hardcore. We can do numerical solutions of Schrödinger's equation. It's not going to change this qualitative behavior. That's what happens. So this wave function looks like that, and this wave function looks like that. And actually, can you guess, based on what we've learned this class, which one has a higher energy? The lower one. I should have drawn them the other way around, so the higher energy one was on top, but oh well. This is higher E. This is lower E. Actually, it's a little bit interesting, because there's one way in which this may not have been intuitive. Where are the electrons in the higher energy state? Right, if I physically draw this, I have a proton, and I kind of have some sort of orbital like that. And the electrons are just this cloud of probability that's located in the center. The electrons are closer together there. They're further apart in this higher energy state. Okay? So the Coulomb energy, which surely there must be there, it was in that U of R1, R2 of the electrons and R1 and R2 of the protons, this full potential where I'm going to write down 1 over 4 pi epsilon naught, E squared, and then I have to have the separation distances 4 times between all the particles. Clearly that is, the electrons are closer together here. There's a repulsion term, which is higher energy. But overall, how do I think of humps? What is the hump? The two humps versus one hump. What is that representing? Kinetic or potential energy? Kinetic, right? Because P is h bar over I d by dx. So momentum, which is going to be, p squared over 2m is kinetic energy, is derivatives of the wave function. So a wave function that's gentle and has one hump has much less momentum, much less kinetic energy than a wave function that has twice the wiggles, the humpiness. Okay? So even though the electrons are closer together, the fact that they have a lower potential, this is a lower energy state than that. And another notion which is important here is that there is no longer one electron associated with one proton. And I mean not just like, you know, this one, electron 2, kind of likes to hang out with proton 2 more than it likes to hang out with proton 1. No, 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 no. In the same sense, well, in a similar or analogous way to the indistinguishability of quantum mechanical particles, there is no state associated with 1 or 2 anymore. You know, when they form a molecule, there's an orbital where the electron goes running around from either one atom to the other. Okay. Hold on, I'm going to hold on to that idea though, because it gets a little more interesting in a second. So that's basically the picture. And a way we draw that is we say, look, this is R, this was A0, and I had the two energies. This is an energy diagram. The energy of the ground state. And it basically split into these two. This is called the higher E is called the anti-binding state. Because basically, this is called the binding state. And you should, so this is the AB, well, I'm not going to write AB on it because that's not a standard abbreviation. This is the anti-binding state and the binding state. The way to read this diagram is the following. This is the energy of the state for the two electrons together as a function of the separation of the particles. The statement that this is not binding is the statement that if I have my two electrons here in this energy diagram, if I move over to here, I'm going to lose energy. This is the energy of the states. This is essentially the potential energy of the state. Sorry. No, that's not the way to say it. This is the overall energy of the system. But if I put the system at this point, it will evolve by rolling downhill, and the energy liberated from that process will go into excess kinetic energy above what they originally had of each atom. And if they can roll downhill, if the system can roll downhill, it will. It always will go from here to here, and that's to say that then you go off to infinity with excess kinetic energy. It's just like this notion of whether an orbit was bound, okay? Even just like, you know, classical mechanics orbits. Rather, on the other side, if I have the two, if I put them at this far separation, and if they're far away, they don't know which way to go. But if they're close enough that they're on this slope, that's to say I'm going to have a chemical reaction, and the two hydrogen atoms are going to fall together and form molecular hydrogen. And that's the way I think of this diagram. And there was one simple point. I had two electrons that split into two, which in some sense was a feature of that I had the two humps, and there was two ways to add two humps. Okay? So that's everything I'm going to say about molecules. Okay? Oh, we're out of time. No, I want to set up talking about not molecules next time. So this, let me say one thing. That's the n equals 1 state. If there was an n equals 2 state, same thing happens. If there's an n equals 3 state, same thing happens. So all the various orbitals that we learned about, in fact, not just the n, there's the L to it. You know, so like in the chemistry, there's the 1s state, the 2s state, the 2p state. When the atoms combine, all those states will split for two atoms in a molecule into two different energy levels. And typically one will be binding and one will be anti-binding. Even though, in fact, that's not a hard and fast rule. I mean, both of them may not bind. There's some atoms that won't bind. Okay? Depends on the details of how this works out. And I'll stop there.